Good morning. Today we are on to I believe it's the third chapter in the course, and the title is The Status of Resources. So we'll start with a bit of an introduction. So one of the commonly cited concerns is that to sustainable development is that much of the resources on which the technological society depends upon are about to get exhausted, or we do not anticipate having much of these resources. So that I want to start the class with that strand of thought and then backtrack a little bit. So when we talk about product process design from an environmental standpoint, that is to minimize the environmental impact, the one area that gets the most attention is global warming potential, greenhouse gas, human activity, and so forth. Now, that's a significant part. Now, there are other aspects to environmental impact. One of these is toxicity. Our activity and our products and co-products and byproducts can have a toxic effect on human beings, on other living things, plants and animals. So that's another aspect of environmental impact. And the third aspect is what we call resource depletion. That is, we may, if we keep using resources at our current rate, exhaust them. This is no different from buying a pecan pie from a bakery, and every night after dinner you eat a slice, and so the pie gets smaller and smaller. Perhaps by the end of the week the pie is no more. Now, I'm not suggesting there's a one-to-one analogy here. Some resources like solar energy is nearly inexhaustible. Maybe it takes billions of years before the thermonuclear reactions in sun come to a halting stop, but we're not going to be around at that point. So, but other things, stuff that we use, like what? Steel, aluminum, natural gas, water, are these going to last forever? So that is an environmental impact of our industrial activity, and this class is taking a look at the status of important resources. We said technologically important resource, right? So like what? When you are at home or at work, you're around computers, other equipment, maybe like printers, filing cabinets at home, refrigerators, dishwashers, microwaves. So you're looking at material like steel, maybe aluminum, copper in the form of tubing maybe. But we also have other material like plastics, Tupperware. We bring our food or store our food. So the ever-present Tupperware is plastic. So as also energy. We need electricity to power our homes and workplaces, and we know that where does electricity come from? Well, it comes from a utility company, but a utility company gets its power from a power plant. This could be a nuclear power plant, or a thermoelectric power plant, or a hydroelectric. So if you peel back, for a nuclear power plant to continue to provide power, it needs to have an abundant resource of uranium, as an example. Or for a thermal power plant, we must have abundant resources of coal. So these are some resources. And then water is something that, whether it's domestic life or industrial or agricultural life, water is important. So these are the kinds of resources that we are going to talk about. Now, if you, as with any other issue, if you talk to your neighbors, your co-workers and so forth, you will get differing points of view about resource availability. Some will be of the opinion that the availability of resources is a legitimate concern, the world is going to end tomorrow sort of thing, and others are going to laugh it off, saying that we have abundant supply of resources. So as is always the case, where does the truth lie? So typically in between. Some resources will last, are predicted to last more than 200 years or more. Not a huge concern. Some are expected to last barely 50 years. Now that should be concerning. So the truth lies in between. We'll see which is more concerning and which is less concerning. Now, so we have to introduce some very important terminology here, technological terminology. One of these is depletion time, another is called mineralogical barrier, and the third is called reserve base. So to set it in context, right, the minerals that we use, the energy that we use, and a lot of water that we use have come from rich deposits that are close to Earth's surface, and therefore they can be mined with ease. When I say close to Earth's surface, it doesn't mean that we can take a spade in a backyard and gain access. You're talking about a few tens or hundreds of feet below the Earth. And when I say rich, what do we mean? It's no different from how you buy milk in the grocery, right? There's whole milk, there is heavy cream, there's 2%, 1%. So a given volume of milk is rich if it has more fat. So if you're trying to churn butter, you have better luck if you're using whole milk than if you are using 1% milk. So the same thing goes with deposits. Say iron ore, right? The rich deposit that typically, and rich deposits typically tend to be close to Earth's surface. Firstly, it's easier to get to them. I spend less energy excavating. But for every ton of material that I pull out of Earth, the yield of iron will be quite high. On the other hand, if it's a poorer deposit, which means for every unit volume, the amount of iron that I get will be less. So that's what we mean by rich and poor. So far, much of our minerals, energy, and water have come to us from rich deposits that are close to Earth's surface, and they can be mined relatively easily. So what happens if we eat into all of this? Well, then we'll have to think about the poorer resources. And these poorer resources, it's a geological phenomenon. For reasons which we don't have to get into here. If you're interested, you can take a petrochemistry class or a geology class. Resources tend to be richly concentrated close to Earth's surface. And then they are available further down, but they are poorer. So once you exhaust this rich deposit, you have to contend with poor deposits. So as we deal with them, it's good to know what their distribution or their availability spectrum is like. Common elements like carbon, nitrogen, etc., they seem to display what is called a log normal distribution. Let me explain what this means. So what you see in the graph here is a log normal distribution. So, this is the ore grade. So we start off from poor and go to rich. So you can think of this side being the surface of Earth. And as you move along the x-axis from far right to the origin, we are moving deeper into Earth, right? So closer to surface, you got rich deposit. The more deeper you go, you have less rich deposit. Unfortunately, there is more tonnage of the poorer deposit and less tonnage of the rich deposit. Currently, our mining activity is shown in this shaded area. This is where we are mining. And so there is a sort of dividing layer in the Earth's surface which kind of separates the rich deposit and the poor deposit, right? It's a conceptual layer, really. So above you got rich stuff, below you got poorer stuff. That imaginary layer is called the mineralogical barrier. Once again, above the mineralogical barrier, and as you move upward towards Earth's surface, you got rich deposits. Below the mineralogical barrier and toward the crust of the Earth, you start having poorer deposit. Again, unfortunately, we have more amount or tonnage of the poorer deposits than we do the rich. Now, this is the kind of distribution that common elements have. Now, the technologically desirable elements like iron and copper and so forth, they display what is called a bimodal distribution. They display a bimodal ore grade distribution. So lots of terms. What's ore? Ore is basically stuff, for want of a better word, stuff that contains what you need, say iron. Typically iron is not in a bulk form. It's in the form of an oxide. it's ferrous oxide or ferric oxide. And then it's not just that, it's combined with other stuff like what? Dirt, mud, broken rocks and so forth. All of that is called ore. So typically that's what we excavate. And then this material, ore, has to be gone through a process called dressing. And it's a technology. Ore dressing is a metallurgical term. It's a process by which the ore is sort of cleaned up, and we separate the iron oxide from the dirt, the mud, the rocks and so forth, and it can then go on to a smelter. So it shows a bimodal distribution. Bimodal means you have two peaks, right? You got the first peak which represents your rich deposits, and then you got a second peak which is more abundant but poorer. And then you got the mineralogical barrier, to this side rich, to that side poorer. So the point is that regardless of which distribution we are talking about, whether you're talking about the log normal or you're talking about the bimodal distribution, fact is thus far human beings have been using the richest deposits. We can get to the poorer deposits but with more effort. And so the amount of rich deposits that lie above the mineralogical barrier is called the reserve base. And that's typically estimated by geological techniques. Again, we don't have to get into the details of it, but geology typically deals with it. So that is called the reserve base. That's the amount of rich deposits above the mineralogical barrier. Now, if we divide this reserve base number by the current usage rate, that is, we use so much per year. If you divide the reserve base by this consumption rate, the result is called the depletion time. Because it's total stuff divided by stuff you use per year tells you how many years you have, right? So depletion time is a quantity that's expressed in years, and it reflects the amount of time in which a resource at constant use rate will be exhausted. So suppose we're talking about copper, and let's say, I'm just making this up, the depletion time is 60 years. Does it mean we won't see copper after 60 years? No. It just means that there is no new source of copper. We may continue recycling and reusing copper. So, when we use the word exhaust, I don't mean it'll just be gone from our everyday use or memory. It's just that you wouldn't have any new source. What is alarming, as geologists and petrochemists have calculated depletion time, is that for a lot of materials, the depletion time is under an average human lifetime. So you got to be careful about how we use this stuff. Let's look at some examples of what this looks like. In this table, as you can see, some materials are referred to as being abundant. So if it is more than 100 years, for example, coal, iron, etc., are anticipated as lasting more than 100 years. Should we not worry about them? I don't think so. I mean, we should always be prudent, right? But we don't have to lose sleep over it. But if I were a business person, I would still pay attention to how much material I'm using, because the more iron I use to provide the same function, my production costs go up. And so I lose a competitive marketing advantage. Or if you're building homes, if you build a green home using LEED's principles, it consumes less energy. And it gives me a marketing advantage over my rival construction professional, right? So now if it is plentiful, it's between 50 and 100 years. Constrained, if it is between 25 and 50. And then rare is less than 25 years. If you look at this, gold, silver, mercury, lead, sulfur, zinc come under that category. So back to the old question, are those who are alarmists wrong? Or are those who think there is no problem wrong? The answer is what you're talking about. If you're talking about the rare and the constrained, yeah, there need to be alarmed. But if you're talking about the abundant, you don't have to lose sleep over it. So this is useful to know because we're talking with facts, right? We're not just whipping up passions emotionally.